Hey, we have seen computation and the method we used for that to convert our governing equation, that was ordinary differential equation, into the algebraic form. We used the first principle of calculus. This method is also called as Euler's method, the great mathematician. And in discussion of computational fluid dynamics, his name will come time and again. Very often you will get to hear about Euler. So now what we are doing here is that we could, and one thing I want to tell, that we could apply the first principle of calculus, that is the approximation of dv by dt as vi plus 1 minus vi upon ti plus 1 minus ti, because we had a first order first degree differential equation. So I told you that when we will have complex examples and when we will see the real computational fluid dynamics, we will not have first degree first order ordinary differential equation. So we will not be able to apply this mathematical law, that is the first principle of calculus, to get our algebraic equation. We'll see other mathematics laws as well. So right now what why we are at a whiteboard is to find the exact solution, as I told you. So we'll find the exact solution of our problem, and we'll see that what values we are getting, and then we will match it with we'll in fact plot a graph, we'll match it with the computed solution, the solution that we got after converting the differential equation into algebraic form. Again, that was not the exact solution. That was there was an error. I told you also, I discussed that there was an error in the solution. And since we have a simple ODE, so I thought that why not get the exact solution and compare the results and see that how much difference we get. So let's start doing that. Okay, so now here the problem was that we had a ball and mass m, there was a force kv and mg, and this ball was having a downward acceleration a. The differential equation that we had was dv by dt is equal to g minus k upon m into v. So first of all, this k by m, I'm going to, because this is a constant, I'm going to call it as another constant, k dashed. So this k by m I'm going to write as k dashed, and we know that its value, in previous episode we saw that this k is 6 pi eta r by this k is 6 pi eta r, and eta is coefficient of viscosity of air, divided by mass. Mass we took as 10 grams, radius we took as 1 meter. I told you I'm not taking a realistic ball falling here, I'm just taking the values where the calculations are simpler. So because I have not told you MATLAB yet, when we'll tell MATLAB, then we'll not have to do hand calculations, then everything will be doing by that. And talking about MATLAB, I just remembered that for in the life of an engineer, after a pen and a piece of paper, MATLAB is the third most important thing. In fact, laptop comes first to run a laptop, so run MATLAB. So MATLAB becomes the fourth important thing. So anyways, yeah, this value I was talking about, with the values when we plug in, this value was 3.4 by 100, or 3.4 into 10 power minus 2. I just write like this, it makes me calculate easily. Anyways, so this is what we have. Now this is k dashed. Now this whole part I'm going to write here, and this equation becomes dv upon g minus k dashed v is equal to dt. Now we will integrate both sides. The integration of this will be ln g minus k dashed v upon minus k dashed, that is equal to t plus some integration constant c. This comes here, so we are going to get ln g minus k dashed v is equal to minus k dashed t plus c k dashed. And this c k dashed is another constant, so why not we call it as a constant? That is, sorry, this k dashed here, we know that this is minus k dashed will be here. So yeah, so I was saying that this c into minus k dashed is another constant, so why not we write it as minus c dashed, some new constant. So this equation is, in place of this minus k dashed into c, I'm going to write as c dashed. Alright, so once we have got this, now we have to find the value of c dash, the constant, and for that we have the information. When time is 0, velocity is 0, so I'm going to put t and v as 0, so we are going to get ln g, this v becomes 0, is equal to, this is 0 to c dash, so c dash is ln g. So this whole equation is going to look like ln of g minus k dash v, g minus k dash v is equal to minus k dash t plus ln g, right? So this thing I'm gonna bring here, so we'll get ln g minus k dash v minus ln g is equal to minus k dash t. Now ln a minus ln b is ln a by b, so if I do this, I'll get ln 1 minus k dash by g into v is equal to minus k dash t. If I remove ln, you know that ln is this logarithm with base e. So we are going to get 1 minus k dash upon g into v is e to the power minus k dash into t, right? So this this v from this equation, or k dash upon g into v, we can write as 1 minus e to the power minus k dash t. So the v we can write as g upon k dash. Now see, this is exact solution here. We have v explicitly in form of time as a function of time, sorry, not in form of time. So any value of time we can put and we can get the corresponding values of v, right? So one thing you can understand, if you remember the computation that we did in the previous episode, there as we saw that at v160, 180, you know, our value was converging towards a constant. So when we had this, we had vi plus 1 is equal to vi plus 10 minus 3.4 by 100 into vi into ti plus 1 minus ti. This is what we had. So just write neatly here, right? This whole thing, this thing was getting this right like this. Alright. So yeah, that's what we have got. So you see that as time was approaching towards 160, 180, this whole portion was becoming 0. This value was decreasing, right? Because vi was increasing. So we are reaching towards a constant value, and if you remember, that constant value was somewhere around 294. So here also you see that at sufficient time, if the ball is allowed to fall for a sufficient time, that when t tends to infinity, you can see that v tends to a constant. This part becomes 0, and v tends to a constant value g upon k dash. And if you take g as 10 and k dash is 3.4 by 100, so 100 comes here, you are going to get 1000 by 3.4, which is approximately going to give us value 294.11. So we understand the value at which our computational value was converging. Our exact value is also converging towards that constant value. And here you can understand by physics, because mg and kv are acting. So as time passes, v is increasing. So this force is increasing. A time will come when this force will become equal to mg, and at that time there will be no net force, and the velocity will remain constant. We also call as terminal velocity. So that's what this terminal velocity, that visualization we are getting here mathematically. In exact solution also we see that at time tends to infinity after a sufficient time, which means the value of velocity will be somewhere 294.11, a constant value it will approach g by k dash, which gives this value. While doing computation also we saw that as we are approaching towards t 160, 180, we are getting the value of velocity close to 294, and the values were very close to that. So if I just bring the table here for you, this was the value. So you can see that at later times, this is how the velocity was using computation. Also the velocity was reaching exactly somewhere around 294, approximately that value. So what we understand that in exact solution also and solution by computation also, there is the same value. But now what I'm interested in is that I want to plot a graph. And I want to plot v versus t graph of this particular situation for exact values, that is the values that we are going to get from the closed form analytical solution, and the values that we computed. So let's do that. For that I need values. You can again say that if you have to calculate values, then I have to put different times and calculate different velocities. No, I told you we'll use MATLAB. So I will teach you MATLAB how to use that MATLAB and solve these kind of equations, input some values of t and getting some values of v as output. Once you feed this in MATLAB, MATLAB will do the calculation for you. So don't worry about calculations right now. One more thing that you have, that when I told you that I took a step size of 20, and if you have to calculate for smaller step sizes, then will you have to do the calculation again and again? No, we'll do all the calculation part, we'll do on MATLAB. So don't worry about that. So okay, now whatever values we have, I have calculated some values for this also. So I have the paper, these values we had already calculated. So let's bring those. First of all, I'll draw the v versus t graph for what we get from exact values. So I need my paper, so I'll take it from here. So here it is in front of me. Yeah, so when I put the values at t equals to 0, for exact, first of all I'm drawing the graph of exact, this red colored graph, this will be for the exact solution. So when t is 0, we know v is 0, so this is the point which will be marked. When t is 20, So V20 that we get is 144.11 meter per second. So this point somewhere here is, I'm gonna plot it, point it. Then we are going to calculate V60. So V60 by this comes to be, when I put the value of t as 60, V60 comes to be 220.58. So I will plot it somewhere here. Now V80 comes to be 255.87. So this is where that value gets plotted. That is, we got V60 we got. So we have V20, we have V40, we have V60, now V80. So when time is 80 seconds, by this method we get the value as 274.99. V100, that is when time is 100 seconds, we get the value of velocity as 285.28. At V120, that is when time is 120 seconds, the value of velocity we get is 289.40. So you see that I'm plotting. And then V140 comes to be 291.75. V at time t equals 160 comes to be 292.93, and V80 comes to be 293.52, and somewhere here I have 294. So this is where the values are converging. You can see here, this I showed when t tends to infinity, this is the value of V converges towards 294.11. So if I join all the points, this is how my graph is going to look like. Now I will get back the computed numbers that we have got and plot the graph. On the same graph I'm going to do that. So I have the values here on the same paper. Again, for computed, we knew that V0 was 0. Let's bring the table here also, so you can see from the table. I'm reading from the paper here. So V0 was 0. V20 we calculated 200. So this is where I'll plot 200. V60 284.48. V80 was 291.03. V100 was 293.13. V120 293.13. 293.80. Sorry. V140 was 294.01. V160 is 294.08. V180 was 294.10. So I can compute it till time t equals to 180 seconds. So you see, this is the graph. So you can see a very beautiful thing now. They both started at same point. That initial condition was same in, when we started computation or when we're doing by exact solution. Converging, they're both of them, they're meeting the same point towards the same constant velocity, towards the value approximately 294 somewhere. But one thing, there is a gap here, right? That this gap that you see, this is the error. Exact solution is that's true solution. But this is the error that we have got due to computation, because I told you again, because this was the slope of the VT graph, and we assumed, because dv by dt is delta v by delta t with limit delta t tends to 0. So I told you, if you take smaller step sizes, if you take step size of 10, the graph will be something like this, somewhere in between these two graphs. If you take a step size of 5, it will be again closer towards the exact graph, right? Whatever graph we got by exact values. Or if you take step size, 2 seconds. If you keep on taking smaller step sizes, you will keep on getting the graph, the curve that you will get, will be closer towards the exact solution. So you understand, this gap is your error. So now what we have to learn is that we have to learn that how do we remove errors, and definitely this we can do. No matter how small step size you take, there will be error, right? Because you will never get exact value. So what to do in that case? Because here you can find exact solution and you can compare. So you are safe. But most of the time you won't be able to find the exact solution, and at that what you have to do is depend on computation. So you can take small step size, but there will still be error. It will not be exact. So we have to take care of those cases. We'll learn. And so we have to learn that, and we also need to learn that how do we do computations with, how do we do these calculations with MATLAB. So if you have to calculate with a step size 10, how do you do with MATLAB with different step sizes, or these kind of equations? If you don't have to use calculator every time and for every t calculate velocity v. So I'll teach you MATLAB for that. One thing that is very important here, before we go back to go to MATLAB and start doing this, do you see the values of velocity here are very high? Like 294.11 is constant. The values are 144. It's more than 100 meters per second. In kilometers per hour, it's even more. And there is something that is missing here. Now let me tell you what is missing. So when I was taking the simple model, there's nothing wrong with all these discussions that we are having since last 2-3 episodes. There's nothing wrong with that. When we used for drag, we used Stokes' formula, all right? That is, we took the dependency of drag force on velocity to be linear. But understand one thing, that Stokes' formula is valid for small velocities, not high velocity values like this. And at high velocity values like this, drag force is directly proportional to v square. So where we made mistake, we made mistake at when we were modeling this, right? We took one force as mg and we took another force as kv. When we applied the signs, this is where now, because we see these values of velocities coming, we understand that there is a fault there, right? So even I worked with some model. So I worked with Stokes' law. I took the drag force to be kv, but we see that the value of velocity is very high, and in these cases Stokes' law is not valid. So I'm not saying that all the discussions, all the learnings we had is not valid. That is cool. Whatever you learnt is perfectly fine. I'm only saying that because the values of velocities are very high that we see, there is some tweaking that we need to do in this model, and this law of science will not be applied there. So in next episode, before we go back to MATLAB, I'm going to talk about modeling a little bit. And the first step was finding the governing equation. So even before that, there is something when we do the modeling, where we choose that what laws of science to apply in what conditions. Like now we understand that this was so everything will be same. The process will be same. Only this formula here needs to change. Why? Because we observe after calculation that the value of velocity is very high. So we can't work with this. So next episode we'll talk about this particular thing, and then we'll go back to MATLAB and proceed with our discussions of computation, and finally we'll land up to talking about computational fluid dynamics. So we are still warming up. So have a nice day.